Well, so in my earlier lecture I was talking about conjugate directions and conjugate curves, conjugate directions and conjugate lines. So, we define them through the condition that if the direction along one curve is dui, suppose this is one direction and along this direction I have the derivative as d, and along the other curve suppose the differential operator is del. So, if dn dot delta r is 0, so d is the differential operator along the first curve, del is the differential operator on the second curve, then dn dot dr means that the two curves are conjugate to each other. Then the curves are conjugate to each other. This definition will be incomplete unless you specify that d is a differential operator on one curve, del is the differential operator on the other. So, you must complete by writing where d is the differential operator along the first curve and del is the differential operator along the second curve. Now, if you want to see this condition in terms of bij, then you expand it. dn can be written as ni dui and del r can be written as rj del uj. So, this must be 0. So, I and j both are dummy indices. So, expanding them you will be getting ni dot rj into dui delta uj equal to 0. On since ni dot rj is bij, so bij dui delta uj is 0. This is the condition. On further expanding it, you will be getting b11 into du1 delta u1 plus b12 du1 delta u2 plus du2 delta u1 plus b22 du2 delta u2 equal to 0. So, this is the condition for two curves to be conjugate to each other. If their tangents are conjugate, we say that the two directions are conjugate directions. The relationship one can see from the first line that this relationship is a mutual relationship. If curve 1 is conjugate to curve 2, then curve 2 is conjugate to curve 1. So, this is that is why we say that the two curves are conjugate to each other. And this condition is similar to the condition of asymptotic lines. So, what follows from here is a note in fact. So, you can note it down that asymptotic lines are conjugate to themselves, or they are self conjugate, are self conjugate. Now, the next question that comes to our mind is what happens when the two curves are parametric also. So, two parametric curves are conjugate to each other if b12 is 0. So, this is the condition. So, this you can write down as a proposition. Two curves over a surface are two parametric curves. Yeah, I should write like this. Parametric curves. Parametric curves over a surface are conjugate to each other, of course. That is understood from the above note, from the note I have written earlier. Parametric curves over a surface are conjugate if and only if this B12 is 0. This condition is easy to establish from this defining relationship. This is the defining condition for curves to be conjugate to each other. So, suppose I have parametric curves which are conjugate. So, if parametric curves are conjugate, then what will happen? For u1 curves, what will happen? Let us see roughly. For u1 curve, delta u2 will be 0. If I consider u1 curve, then du2 will be 0. Okay. And for u2 curve, for u2 curve, what I will do? I will take the differential operator as delta. So, delta u1 will be 0. So, if parametric curves are conjugate to each other, then du2 will be 0 and delta u1 is 0. So, du2, if I put du2 over here equal to 0 and delta u1 equal to 0, then you will see that the first term becomes 0 because of delta u1 over here, and this term will be 0 as well as the last term will be 0 because of du2. So, you will be getting B12 into du1 delta u2, sorry, B12 like this. This is 0. Now, in this last equation, either du1 is 0 nor delta u2 is 0. So, and this expression 0 means B12 is 0. So, if parametric curves are orthogonal, are conjugate, then B12 is 0. So, the observation is true one way. The other way, if B12 is 0, then what will happen? You will be getting B11 du1. So, then from the conjugacy, then by conjugacy condition, what you will be having? You will be having B11 into du1 delta u2 plus B22 into du2 delta u1 delta u2 equal to 0. So, if B12 is 0, then you get this. And if you look at the last equation, you will notice that this equation is satisfied by du2 equal to 0 and delta u1 equal to 0. That means, the parametric curve satisfies this equation. du2 is 0 means this term become the last term, okay, and delta u1 is 0. So, no, I have written it wrongly. This is delta u1. I am sorry. So, you can easily notice from the last observation that the parametric curve satisfy this equation. So, it is easy to see that parametric curves satisfy the above equation, and that means they are conjugate to each other. So, that is parametric curves are conjugate whenever B12 is 0. So, the statement is true from both sides. So, this proves the proposition completely. Yes.
Orthogonal parametric curve are conjugate,
B12 and G12 both will become 0. So, these things you can see by yourself. There are many relations which you can see. Okay. Now, what we will be doing today, we will look at some of the problems. For example, some of the surfaces are written in explicit form and implicit form. So, we will see how can we think of the asymptotic lines, conjugate direction, etc. For other surfaces, I discussed one example, but for a surface which is in the implicit form, the question is what will be the asymptotic lines, etc. So, this is one of the example that I will be doing for the surface given in parametric, given in implicit form f x y z equal to 0, find the asymptotic lines, etc. For asymptotic lines, the condition is that dn dot dr is 0, or I say second fundamental form is 0. So, what I will be doing, I will finding out the dn as well as dr. So, if you remember that when we were resolving the issue of second and first fundamental form, etc., we consider the differential of f. The differential of f is written as f x into dx plus f y into dy plus f z into dz equal to 0. Okay, and from here you can see that the normal n, what follows from here is that the normal n, this differential is in fact the tangent plane at okay, tangent I will discuss later on. You can always convert an implicit equation into explicit equation, provided one of the partial derivative of f is non-zero. So, if I assume that suppose f z is non-zero, then this equation is written as z equal to some other function small f of x y, and from here you can see that dz equal to f x into dx plus f y into dy, okay, where f x and f y means partial derivative with respect to x and y, same over here also. So, if these equations, if this and this equation represent the same curve, then their derivative will also represent the same tangent plane. Let me call this as 1 and this as 2. So, on comparing the coefficient in the 1 and 2, what do you get is that f x upon f x is equal to f y upon f y equal to f z upon minus 1. Okay. So, this gives me f x equal to minus times f x upon f z, and small f y is minus times f y upon f z. If I write down the position vector as x y z, then R 1 you can see is 1 0 f x, and R 2 is 0, sorry 1, r 1 means 1 here, 0 here, 0 1 f y, and therefore, from these two you can find out r 1 cross r 2, which will give you the normal. So, the normal from here will become minus f x, and this is minus f y and 1. And therefore, I can write down the normal for the surface represented in implicit form. So, the normal first of all r 1 cross r 2 will become minus f x, means if you look here it will be f x upon f z, this will be f y upon f z, and here you have 1. This can also be written as 1 upon f z into f x, f y and f z. And now I can talk of the normal n, unit normal n. So, I can write down normal f n as f x, f y, f z into 1 upon under root f x square plus f y square plus f z square. This is the normal. Okay. And therefore, I can write down d n. The derivative of the normal is 1 upon under root this quantity. Since it is a unit vector, so we do not look at this denominator. It will be d f x, d f y and d f z. Okay. You are differentiating. So, these are partial derivatives, and dr I can write down directly from here. Okay. So, dr will be dx, dy, dz, and for asymptotic lines the condition is that d n dot dr is 0. So, d n dot dr must be 0. So, that will give me equal to dx, sorry, dfx, dfy, dfz into 1 upon under root something dot dx, dy and dz. So, for asymptotic lines, what should happen? d n dot dr must be 0, and therefore, if I put the right hand side of this thing to be 0, so this under root will go off. This implies that dfx into dx plus dfy into dy plus dfz into dz equal to 0. So, this gives you the asymptotic lines on the surface whose equation is given in implicit form. Now, at this point you can resolve the question of asymptotic lines for a surface z equal to f x y. Okay. So, if the surface is represented by explicit equation, you have to go along the same computation, and you can write down the version for small f also. So, find the asymptotic line if the surface is given in this form. Find the asymptotic lines for the above surface.
So, will be saying the both?
No, it will involve small f, not the same as capital F. You have to keep all your expression in terms of small f. Okay. I have converted the expression of small f into capital F. You do not do that. Keep all expression in terms of small f and compute dn, compute dr, and write down the equation. Okay. This much can be done easily. Now, there are many other problems. As a particular case, you can take up as a particular case, find the asymptotic lines, find the asymptotic line for z equal to x to the power 4 plus y to the power 4. You can see here the equation is given in explicit form. Once you do it in general, you can do it for this also, but if you find this easier, do it first and then you try to generalize it. Okay, it is up to you. And then we have some other, these were the only two, and we have some questions for conjugate family of curves also. So, I will leave these exercises for the students. These are some simple exercises. This we have done for perhaps principal directions or lines of curvature. Now, you have to do it for conjugate family of curves. On the surface, given in parametric form u square plus v square, find the conjugate family, find the conjugate family of the curves u square plus v square equal to c square. Okay. So, this is the question. I have dealt with this surface in finding the principal directions and lines of curvature. Now, you have to make a little change. One operator is d, other operator is del, and then work out conjugate family of curves. Okay.
So, we have to solve the dn dot dr 0, that equation.
dn dot delta r.
Delta r 0.
Yes.
Solve the equation and
that will give you some equation, that will give you a family of conjugate family. That is the only change and nothing else. Prove that the principal direction bisect the asymptotic direction. Perhaps we have worked out the formula for angle.
Yes, sir.
Okay, so this can be done from there. Prove that the principal directions, prove that the principal directions bisect the asymptotic direction, bisect the asymptotic directions. This is interesting in fact. Show that the mean curvature is 0 on the surface whose asymptotic lines are perpendicular. And if you remember that the mean curvature will be BII, and for perpendicular case what will happen? B12 and G12 both become 0. So, that will prove the assertion. This is
The second problem we have done, I think. Bisect.
if we have done so, okay.
We have done like.
Okay, if we have already done so, no problem. So, show that the mean curvature is 0 on a surface whose asymptotic lines are perpendicular. If you know the behavior of Bij's and if you know that the mean curvature is Bii, that is the sum of B11 plus B22, then you can answer this question immediately. So, the understanding of mean curvature and Bij and some other condition like orthogonality of the asymptotic directions and Bij condition of Bij. I hope I will stop at this point. So, these are the exercises which are interesting and simple. So, students can do by themselves. So, this finishes the content of this syllabus, and difficulties are being discussed by Dr. Akhlat. If still you students have problem, they can contact me as well. So, I stop at this point.